In this lecture, I'd like to talk about latent heat and then do some calorimetry problems together. So first of all, a phase change we define as when a substance changes from one form to another. We're pretty familiar with this phenomenon from everyday life, right? Water boils. When it boils, the liquid becomes a gas, right? So it goes from liquid water to steam. So that's one common one, right? Liquid to gas is boiling. You could also go from a solid to liquid. If you have a cube of ice and you leave it out on a common surface or whatever and wait a little while, it'll melt and turn to liquid water. So melting is when something goes from solid to liquid. So that's some common phase changes that we're used to thinking about. Now, one thing that you might not know is that while something is changing phase, it holds constant at a specific temperature. For example, if you're boiling water at sea level, that happens at 100 degrees Celsius. If you have a pot of water and it starts to boil, the pot of water will sit there at 100 degrees Celsius, even as you add more and more heat, say from the fire underneath it that's caused it to boil in the first place, right? It'll still sit there at 100 degrees Celsius, even as you're adding heat, until the water's all boiled away, all right? So, no change in the temperature of a substance while something is undergoing a phase change. That's why it's called latent heat. See, latent means hidden, okay? So the hidden heat is the amount of heat that you have to add to get the thing to change phase completely. Now, different substances react differently to the energy added or removed during the phase change, and this is because of the structure of the surface itself. They have different internal molecular arrangements. The amount of energy also depends on the mass of the sample. Of course, it takes a lot more energy to boil away, 1,000 kilograms of water than it does 1 kilogram of water. So, if we're talking about the amount of energy Q that's required to change the phase of a sample of mass M, then we define the latent heat, or the heat L, as Q over M, okay? So this latent heat of the material, L, right, which is Q over M, is the amount of energy per unit kilogram that it takes to change the phase, for whatever phase change that you've got. Now the energy required to change that phase, Q, is equal to plus or minus mL. You choose the plus or minus sign depending upon the direction that you're going with the phase change. We call these latent heats, but there's different latent heats depending upon what process is taking place. We call it the latent heat of fusion when the phase change is from solid to liquid or vice versa. So if something is freezing or melting, you'll use the latent heat of fusion for that process. We call it the latent heat of vaporization when the phase change is liquid to gas or vice versa. Okay? So if something is boiling or condensing, then you'll use the latent heat of vaporization. Its Q is equal to plus or minus mL, depending on which way you're going with the phase change. You use the positive sign when the energy is transferred into the system, which results in melting or boiling. We use the minus sign when energy is transferred out of the system, and that results in freezing or condensation. So I always think, do I put it in the fridge or do I put it on the stove to get that thing to happen? If I put it in the fridge, its Q is minus mL. If I put it on the stove, it's Q plus mL. Here's some latent heat values for some different substances. We've got water here, okay? Water, the melting point is, of course, 0 degrees Celsius. And if you're talking about going from liquid water to ice, then you use the latent heat of fusion. And that's 3.33 times 10 to the 5th joules per kilogram. Now, the boiling point of water is 100 degrees Celsius, okay? If you're talking about going from a liquid to a gas or back again, then you use the latent heat of vaporization for that. And the value for water for the latent heat of vaporization is 2.26 times 10 to the 6th joules per kilogram. You can see that these numbers aren't the same. The latent heat of vaporization is much larger by an order of magnitude than the latent heat of fusion. And that's kind of how I think of it as, if you're going from a solid to a liquid, you're kind of weakening the bonds between neighboring water molecules, but you're not getting rid of them entirely. But if you're talking about going from a liquid to a gas, well, now those water molecules are so far apart that you can kind of consider the bond in between neighboring water molecules to be broken altogether, and that takes more energy than weakening it. That's just how I envision it. So here's a little plot for what's going on. On the vertical axis, you can see the temperature here. And on the horizontal axis, you can see the energy added to the water. Okay, so we're starting off with a small amount of water. And if we start with that water frozen at minus 30 degrees Celsius, right, then what happens is, at first, it's a cube of ice, and it's really cold. You start adding heat energy to it, and as you do that, the temperature of that ice increases, and it goes up from minus 30 to 0. So you can see that it's a straight line, but there's a slope to it between minus 30 and 0. Now see, that's not hidden. You can add heat to the substance, and that results in a temperature change that you can then measure. So there's a slope. Now you reach 0, right? This is where the phase transition happens. Well, at this point, you're going to have that ice becoming water as you add more heat. But that doesn't result in a corresponding temperature change, right? This is the hidden part. This is the latent heat. So you're going to add a certain amount of energy, add, until all that ice melts and becomes liquid water. Now it's all liquid water here, right? Well, at this point, you start adding heat, and now you're going to see that result in a change in temperature. The water is going to start to heat up. So it'll heat up between 0 and 100 degrees C, and you can measure that temperature change all along the way on this plot. Then once it reaches 100 degrees C, that water begins to boil. Now it's hidden again. You have your latent heat of vaporization. And until all that water is boiled away, the liquid in the pot will still remain at 100 degrees Celsius. And so this is the horizontal line that you see all the way across. Okay? Now you can see that the horizontal line for vaporization is a lot more than that for melting right here. Okay? So you've got a smaller amount of energy that it takes to get the ice to all melt than it does to boil it all away. Okay? So that results in a larger area under the curve here. Now, once it's all boiled away, you can start heating it up again, and yet again, measure an increase in temperature, and so you see the slope. So that's how to interpret that plot, and that's kind of what's going on with the physics. Okay, let's do a calorimetry example. A calorimeter is a device where basically you have an insulating material, right? You have very well insulated material, and then you combine things within the calorimeter that are at all different temperatures, okay? And then what happens is you wait, you put it in the calorimeter and you wait, and you measure the temperature all along the way while you wait. And then once the system comes to thermal equilibrium, it'll reach some final temperature where it just sits there. Okay, it's all done. Everything's come to thermal equilibrium, ends up at the same temperature. Then you measure what that final temperature is. You can do this for unknown substances. You can mix an unknown new material with materials that you're not familiar with, and then use that calorimetry experiment to determine the heat capacity of a substance. Or you can verify what you already know, right? So in a lot of calorimetry problems, you're given known substances, right? You're given known substances that start at different temperatures. You allow them to come to thermal equilibrium, and using the known heat capacities, you solve for what the final temperature of the system might be, okay? Or some other unknown variable. So that's more what this problem is. But bear in mind that calorimeters exist out there. They're scientific devices, and they're actually used to measure the heat capacities of unknown substances, okay? So that's what they're for. Let's do this calorimetry problem together. Here we have a 50-gram copper calorimeter, and it contains 250 grams of water, initially at 20 degrees Celsius. So, if you were to do this experiment, how much steam would you have to condense into the water if the final temperature of the system is to reach 50 degrees Celsius? Okay, so that's the question. Now, let's think about this. The steam is going to lose energy to the system by condensing. Okay, so first you're going to have steam. The steam is going to come in. It's going to be at 100 degrees C. It's going to condense and become liquid water. Then that addition of that hot steam causes the water and the copper to heat up. Okay, so in this case, you've got a closed system. Energy isn't going to be lost or gained for the system if it's well insulated. So what we're going to assume is that all the heat energy that comes from the steam is given to the copper and the water that are already in the calorimeter. So if I sum all those contributions to the heat up from everything, the sum of all those heat contributions should equal 0 in a perfectly insulated system. And that's what you have to do most of these calorimetry problems. That's going to be my strategy. So here's my solution. Okay? The copper and the water originally in the container are going to increase their temperature. The steam is going to condense first and then cool off. Now, the final temperature of the system is set, okay? It's saying how much steam to get it to reach 50 C, okay? So here we go. I'm going to sum up all the heats from all the contributions, and I'm going to set those equal to 0, assuming no heat is lost or gained from the system. Basically, it's a well-insulated system. Okay, now, the copper and the water originally in the container, right, are not going to go through a phase transition. They're going to increase their temperature by 30 Kelvin, 30 Celsius. Remember the delta T, it doesn't matter what units you're in because the degrees are the same size. So they're going to increase their temperature from 20 C to 50 C, which is 30 C or 30 Kelvin. So we have the copper calorimeter first, okay? The mass of the copper calorimeter was 50 grams or 0.05 kilograms. Using one of those tables that I showed you earlier, you can look up the heat capacity of copper. The heat capacity of copper is 387 joules per kilogram per Kelvin. Okay? And then you write the temperature change that the copper goes through. It's going to increase from 20 to 50. So T final minus T initial would be 50 minus 20, which is 30. Okay, so we have a 30 Kelvin temperature change here. So my Q is equal to MC delta T for the copper would be 0.05 times 387 times 30. Okay, so that's my first contribution to the sum of the Q's. My next contribution to the sum of the Q's is the increase in temperature of the water that was already in the calorimeter. I had 250 grams, which is 0.25 kilograms of liquid water in there. The specific heat of water is 4,186 joules per kilogram per Kelvin. And the temperature change of the water goes from 20 to 50 Celsius. So T final minus T initial would be 50 minus 20, or 30 degrees C or degree Kelvin change, right? So my Q is equal to MC delta T contribution from the water originally in the calorimeter would be 0.25 times 4,186 times 30. Okay? Now let's think about what's happening to the steam. First, the steam is going to come in and it's going to condense, okay? So that's my latent heat expression. It's minus ml because it's condensing. So heat is getting sucked out, so you use the minus sign. Now, we don't know what the mass of steam is, so I'm going to leave that as my unknown variable minus m steam here. But it's going to use the latent heat of vaporization for water. Looking up that number in my tables, the latent heat of vaporization is 2.26 times 10 to the 6 joules per kilogram for water going from steam to liquid. So my expression for the latent heat for the steam would be minus mass of the steam times 2.26 times 10 to the 6 joules per kilogram. Okay. Now, once the steam has condensed and become liquid water in there, it's still hot. It's going to initially be 100 degrees Celsius because it's just gone through that phase transition. If you want it to reach a final temperature of 50 degrees C, it's going to have to lose 50 degrees C in temperature, okay? Which means that my delta T, T final minus T initial, would be 50 minus 100, which is minus 50 in terms of the temperature change in Kelvin or Celsius. So my expression for the MC delta T for the steam would be mass of the steam times 4,186 joules per kilogram per Kelvin times minus 50. Now, a lot of students make a mistake here, and they put in the heat capacity for steam here instead of the heat capacity for liquid water. But remember that once the steam has condensed, okay, it's liquid water now. So now I'm going to take all these terms here. I think I've gotten everything in my expression in the sum of the Q's. They all sum up to equal 0, okay? And now I'm going to start plugging things into my calculator. The MC delta T for the copper gives me 580.5 joules. The MC delta T for the water originally in the calorimeter is 31,395 joules. Now, I can't directly calculate this here about the mass of the steam because I don't know what the mass of the steam is. but I can't combine like terms, okay? So both of these terms are going to be negative from the minus ml and from the minus 50, okay? And then I can combine the mass of the steam, right, minus the mass of the steam times the 2.26 times 10 to the 6th plus, right, sorry, that should be plus right there because the minus sign is on the outside. Okay, so plus 209,300, which comes from multiplying 4186 times 50. Okay? So when I combine those two things, right, then I end up with 469,300 joules per kilogram. So now I have an algebraic equation. 0 is equal to 580.5 plus 31,395 minus mass of the steam times 2,469,300. With a little bit of rearranging of my algebra, I add this mass of the steam times this constant to the other side of the equation, right? And then solve for the mass of the steam by dividing out by 2,469,300. What I end up with then is 0.013 kilograms of steam. So that's how much steam it takes to get the temperature inside the calorimeter to 50 C. Okay, that's the example. If you're confused about the algebra or any steps here, pause the video at this point and make sure you can follow what I've done. And as always, thanks a lot for watching, and I'll see you in class.